In this video, we'll explore the reactions and versatility of alcohols in organic chemistry. We'll start by reviewing some fundamental properties of alcohols, including their behavior as weak acids and relatively strong bases. Next, we'll discuss a couple of methods for synthesizing alcohols, starting with the synthesis of primary and secondary alcohols from alkyl halides. We'll then explore the oxidation and reduction reactions of alcohols, and finally, cover how Grignard reagents can be used to synthesize alcohols by reactions with carbonyl compounds. Let's start with a quick review of alcohols. Alcohols are organic molecules with the general formula ROH, where a carbon is bonded to a hydroxyl group. These compounds can act as weak acids and also as Lewis bases. Alcohols are typically identified by the suffix OL in their name, like in ethanol or isopropanol. Alcohols are classified as primary, secondary, or tertiary, similar to how we describe a tetrahedral carbon atom based on the number of carbons attached. A primary alcohol has one carbon attached to the carbon bearing the hydroxyl group, a secondary alcohol has two, and a tertiary alcohol has three. When no carbons and three hydrogens are attached to the carbon, we have methanol. Additionally, if a hydroxyl group is attached to an aromatic ring, it's known as a phenol. Alcohols are versatile functional groups that can participate in various reactions we've already covered. The hydroxyl group in alcohols is naturally a poor leaving group and a weak nucleophile and base. However, when treated with a strong base to deprotonate the acidic hydrogen, the alcohol forms an alkoxide ion, which is a much stronger base and a better nucleophile. These alkoxides are excellent nucleophiles for SN2 reactions and serve as effective bulky bases for E2 reactions. Conversely, protonating the alcohol transforms it into an oxonium ion. This protonation converts the hydroxyl group into its conjugate acid, significantly improving its leaving group ability. As a result, it can then participate in SN1 and E1 reactions, and though less commonly, in SN2 and E2 reactions. With this in mind, let's move on to our first reactions for alcohol synthesis, converting methyl, primary, and secondary alkyl halides into alcohols through substitution reactions. For methyl and primary halides, reacting the halide with sodium hydroxide in a dipolar aprotic solvent such as dimethyl sulfoxide, DMSO, will result in an SN2 substitution. This process is most effective for methyl and primary halides. Secondary halides, when reacted with hydroxide, often yield a mixture of SN2 and E2 products, while tertiary halides primarily undergo elimination to form E2 products. Due to these limitations, forming secondary alcohols from secondary halides requires a different approach. To convert a secondary alkyl halide to a secondary alcohol, the halide is first reacted with sodium acetate in a dipolar aprotic solvent, such as dimethyl sulfoxide, DMSO. This is followed by a basic hydrolysis step using hydroxide and water, which ultimately yields a secondary alcohol. Let's break this down. In the first step, the acetate ion acts as a nucleophile, attacking the alpha carbon and displacing the halide as the leaving group. Acetate is more suitable for this reaction than hydroxide because its conjugate acid, acetic acid, has a pKa of 4.76, making acetate significantly less basic than hydroxide. This means that while acetate is a poor base, it remains an effective nucleophile for substitution reactions. This SN2 reaction in the first step results in the formation of an ester. In the second step, this ester undergoes hydrolysis under basic conditions, breaking down to yield the desired secondary alcohol. Hydrolysis involves the reaction of the ester with hydroxide and water, cleaving the ester bond and releasing the alcohol. Carbonyl groups have electrophilic delta plus carbon atoms due to the difference in electronegativities between carbon and oxygen. Oxygen, being more electronegative, pulls electron density away from the carbon, creating a partial positive charge on the carbonyl carbon. This makes the carbonyl carbon susceptible to nucleophilic attack by the hydroxide ion in the second step, forming a tetrahedral intermediate. In this intermediate, the pi electrons from the carbon-oxygen double bond are shifted to the oxygen, resulting in the formation of an alkoxide. As we've previously discussed, alkoxides are strong nucleophiles. In this step, the nucleophilic attack by hydroxide on the carbonyl carbon and the non-bonding electrons on the alkoxide pushing down to expel the leaving group occurs in equilibrium. In the step that restores the carbonyl, The non-bonding electrons on the alkoxide can push down to expel either the alcohol or the alkoxide as the leaving group. Occasionally, the latter occurs, forming an alkoxide ion and acetic acid. The acidic proton from the acetic acid is then quickly deprotonated by the alkoxide, which acts as a strong base, forming the secondary alcohol. Because the first step of this two-step reaction is an SN2 reaction with acetate as the nucleophile, it is important that the substrate does not have significant beta branching. Steric hindrance from beta branching can impede the nucleophile's approach, thereby discouraging the SN2 reaction from proceeding efficiently. Now that we've covered how to synthesize methyl, primary, and secondary alcohols from alkyl halides, let's move on to explore the oxidation and reduction reactions of alcohols. In organic chemistry, the oxidation of alcohols involves breaking a carbon-hydrogen bond and forming a carbon-oxygen bond on the same carbon atom. This process increases the oxidation state of the carbon, converting alcohols into various carbonyl-containing compounds, depending on the type of alcohol and the strength of the oxidizing agent used. With this understanding, let's explore some common oxidation reactions of alcohols. When primary alcohols are reacted with chromic acid in the presence of sulfuric acid, they undergo full oxidation to form carboxylic acids. This reaction proceeds through the formation of an aldehyde intermediate, which is subsequently further oxidized to the carboxylic acid. On the other hand, secondary alcohols under the same conditions oxidize to form ketones, as they do not have a hydrogen atom on the carbon to enable further oxidation. Let's observe these differences through the mechanism of chromic acid oxidation. In the following mechanisms, we will consider the differences in primary and secondary alcohols. In the first step of the reaction, chromic acid is protonated by protons in solution, forming an oxonium ion. This protonation converts the hydroxyl group of the alcohol into an oxonium ion, enhancing its leaving group ability. The nucleophilic lone pair on the oxygen of the alcohol then attacks the chromium atom in an SN2-like fashion, displacing water as the leaving group and forming a protonated chromate ester. This ester is quickly deprotonated by water to yield the neutral chromate ester intermediate. In the next step, a proton on the carbon of the chromate ester is deprotonated by water in the solution in an E2-like fashion. This deprotonation facilitates the formation of a pi bond between the carbon and oxygen, creating a carbonyl group while simultaneously ejecting the chromium group as a leaving group. This reaction results in the formation of an aldehyde from the primary alcohol and reduces the chromium from the formal oxidation state of 6 to 4 as it gains a pair of electrons. Notice that in this reaction, the oxidation of alcohols involves breaking a carbon-hydrogen bond and forming a carbon-oxygen bond on the same carbon atom. Because the aldehyde carbon still has a hydrogen attached, the aldehyde can be further oxidized into a carboxylic acid, replacing the carbon-hydrogen bond with a carbon-oxygen bond in the carboxylic acid. Now let's compare this to the oxidation of secondary alcohols to ketones. When the carbon-oxygen pi bond forms, converting the alcohol to a ketone, there are no more oxidizable hydrogen atoms on the carbonyl carbon. This is why secondary alcohols oxidize only to ketones and do not proceed to carboxylic acids, unlike primary alcohols, which can be further oxidized due to the presence of an additional hydrogen atom on the carbonyl carbon. For this, we use a different set of reagents that act as a milder oxidizing agent. To achieve the oxidation of a primary alcohol to an aldehyde, we can react it with pyridinium chlorochromate, PCC, in dichloromethane, an anhydrous organic solvent. The absence of water in the reaction conditions helps stop the process at the aldehyde stage, preventing further oxidation to a carboxylic acid. Lastly, tertiary alcohols do not undergo oxidation to form carbonyl-containing compounds because there is no hydrogen atom on the carbon bearing the hydroxyl group that can be replaced with a carbon-oxygen bond. Now that we've explored the oxidation reactions of alcohols to form carbonyl-containing compounds, let's move on to the reactions that can reduce these carbonyl compounds back to alcohols. We've learned that oxidation involves breaking a carbon-hydrogen bond and forming a bond to oxygen at the same carbon. In contrast, reduction reverses this process by replacing a carbon-oxygen bond with a carbon-hydrogen bond. This is typically achieved through metal hydride reductions, which can be performed using two main types of reactions. In these metal hydride reactions, atoms with lower electronegativity than hydrogen, such as boron or aluminum, are commonly used. The difference in electronegativity imparts a partial negative charge to the hydride, giving it H- character. This allows the bonding pair of electrons to act as a nucleophile, enabling the hydride to attack electrophilic centers like carbonyl carbons. Let's take a look at both of these reactions. The first reaction involves reacting a carbonyl of an aldehyde or a ketone with sodium borohydride, NaBH4, in ethanol, followed by an acid hydrolysis in the second step. Let's break down the mechanism for this reaction. In the first step, the nucleophilic bonding electrons of the hydride ion attack the electrophilic carbonyl carbon of the aldehyde or ketone, pushing the pi bonding electrons onto the oxygen atom. This results in the formation of an alkoxide ion. The alkoxide can then act as a nucleophile, attacking boron in BH3 in a Lewis acid-base reaction to create an intermediate complex. This intermediate can subsequently react with three additional aldehyde or ketone molecules, leading to the formation of a tetrahedral intermediate structure, a tetraalkoxyborate. The second step involves acid hydrolysis of the tetraalkoxyborate intermediate to regenerate the alcohol. In this step, a non-bonding electron pair on one of the alkoxide oxygens deprotonates a hydronium ion present in the solution. This protonation creates a much better leaving group, which subsequently departs at allowing the intermediate to decompose and release the corresponding alcohol. Following this, water attacks the boron atom in a Lewis acid-base reaction. The resulting oxonium ion is then deprotonated by another molecule of water, forming a stable intermediate. This intermediate can undergo the same reaction sequence a few more times, ultimately yielding all the corresponding alcohols. The second reaction used for metal hydride reductions involves reacting a carbonyl of an aldehyde or a ketone with lithium aluminum hydride LiAlH4 in diethyl ether, followed by an acid hydrolysis in the second step. The reaction mechanism for this reduction follows an analogous method to the sodium borohydride reduction, so we won't cover the mechanism in this video. Both NaBH4 and LiAlH4 are capable of reducing aldehydes and ketones to their corresponding primary and secondary alcohols. However, LiAlH4 is a much stronger reducing agent and can reduce carboxylic acids to primary alcohols, while NaBH4, being a milder reducing agent, is not effective for these reductions and is typically only used for aldehydes and ketones. The final reaction for alcohol synthesis we'll cover is the formation of alcohols through the reaction of Grignard reagents with carbonyl compounds. For a more detailed explanation of Grignard reagents and their chemistry, check out my other video linked on the screen. Grignard reagents are strong carbon-based nucleophiles that are highly effective for forming carbon-carbon bonds. They readily attack the electrophilic carbonyl carbon in compounds such as aldehydes and ketones, resulting in the formation of alkoxides. These alkoxides are subsequently protonated in an acid hydrolysis step to yield the corresponding alcohols. Depending on the carbonyl compound it reacts with, Grignard reagents can produce alcohols with varying degrees of substitution. For instance, when a Grignard reagent reacts with formaldehyde followed by an acid hydrolysis, it results in a primary alcohol. Reactions with aldehydes or ketones, followed by acid hydrolysis, yield secondary and tertiary alcohols, respectively. As always, let's do some practice. Propose reaction sequences to accomplish the following transformation. Specify necessary reaction conditions and reagents. You may use any building block with less than or equal to 2 carbons for your syntheses. However, the reagents that you use that are not incorporated into the final product may contain more than 2 carbon atoms. The structure of the reactant and the product should be shown for each chemical transformation. Feel free to pause the video and try these problems on your own first. In the first reaction, a secondary halide is converted into a secondary alcohol with an inversion of configuration. This transformation involves reacting the halide with sodium acetate in a dipolar aprotic solvent, such as dimethyl sulfoxide DMSO, followed by basic hydrolysis with hydroxide in water. And the second reaction, we see a primary bromide being converted into an aldehyde. Direct conversion from a primary bromide to an aldehyde in a single step isn't possible, so this synthesis requires multiple steps. For tackling multi-step synthesis problems, using a retrosynthetic approach can be highly effective. Retrosynthesis involves breaking down the target product into simpler intermediates that logically connect back to the starting material. Let's apply retrosynthesis to map out the steps for this conversion. Going one step back from the aldehyde, we might have had a primary alcohol that was oxidized to form the aldehyde. From there, we know how to convert primary halides to primary alcohols, which leads us back to our starting material. Using this retrosynthetic analysis as a guide, we can now determine the appropriate reagents to move forward toward the product. In the first step, we can synthesize the primary alcohol from the primary halide through substitution using sodium hydroxide in a dipolar aprotic solvent such as dimethyl sulfoxide via an SN2 mechanism. The primary alcohol can then be selectively oxidized to an aldehyde without further oxidation to a carboxylic acid using pyridinium chlorochromate PCC in dichloromethane. In the third reaction, we observe the reduction of a ketone to a secondary alcohol. This can be accomplished using either sodium borohydride in ethanol, followed by an acid hydrolysis, or lithium aluminum hydride in diethyl ether, followed by an acid hydrolysis. In the fourth reaction, 4-bromobutene-1-ol is converted into a lactone. While this transformation is more complex, applying a retrosynthetic approach can help guide us in determining the necessary steps to solve the problem. Let's draw the retrosynthetic arrows to trace one step back. The formation of the lactone likely resulted from an intramolecular SN2 reaction, where the nucleophilic carboxylate oxygen attacked the electrophilic alpha carbon, displacing the bromide as the leaving group. Going another step back, protonating the carboxylate restores the carboxylic acid. From there, we can recall that a primary alcohol can be oxidized to a carboxylic acid, which brings us back to our starting material. Using this retrosynthetic analysis as a guide, we can determine the appropriate reagents to move forward toward the product. First, we oxidize the primary alcohol to a carboxylic acid using chromic acid in the presence of sulfuric acid. Next, rotating the molecule can position the bromide-bearing alpha carbon near the carboxylic acid. To create the nucleophilic carboxylate, we deprotonate the carboxylic acid using a base such as sodium hydroxide or sodium hydride in a dipolar aprotic solvent like dimethyl sulfoxide. This setup favors the intramolecular SN2 reaction, leading to the formation of our lactone product. In the final reaction, a cycloalkene is transformed into the given alcohol. While this transformation is complex, applying a retrosynthetic approach helps in determining the necessary steps to solve the problem. First, we count the number of carbons in both the starting material and the product. The product has 8 carbons, while the starting material has 6, indicating that a carbon-carbon bond formation occurred during the transformation. To achieve this, we can utilize a method from our reaction toolkit, Grignard reagents. A Grignard reagent reacting with an aldehyde forms a secondary alcohol after an acid hydrolysis. Therefore, one logical step back from the product is to consider the intermediate Grignard reagent formed from a bromide. At this point, we observe that the bromine is located at the allylic position. This suggests that allylic bromination could be used to achieve this intermediate, bringing us one step back to the starting cycloalkene. Using this retrosynthetic analysis as a guide, we can outline the appropriate reagents to move forward toward the product. First, we perform allylic bromination using NBS in the presence of light and peroxides, with carbon tetrachloride as the solvent. Next, the bromide can be converted into a Grignard reagent by reacting it with magnesium in diethyl ether. This Grignard reagent then reacts with acetaldehyde to form a secondary alkoxide, which is subsequently protonated during the acid hydrolysis to yield the desired alcohol product. As always, thank you for watching, and I'll see you next time.